In this lesson, we are going to learn about standard reduction potentials and how we can use a table of standard reduction potentials to determine if a substance undergo reduction or oxidation. But before we talk about the standard reduction potential, let's look at the shortcut to memorize what is oxidation and what is reduction. We have Leo the lion says grr. Now Leo, the L represent losing electrons. That's what the E is for, electron, and O is for oxidation. So in oxidation, you have lose electron. For the grr, we have G is going to be the gain, E is for the electron, and R will be your reduction. So keep that in mind. Leo the lion says grr to memorize what is reduction and what is oxidation. So if the standard is in reduction, that means it will be in the format of gaining electron. Now if we look at the table is arranged in the decreasing order of standard reduction potentials. And again, going back to the name, it says standard reduction potential, so all the potential will be given in reduction form. So let's say if we have two substances here, we have aluminum and iron, or Al and Fe. By looking at the standard reduction potential of both substances, you can determine if a substance will undergo reduction or oxidation. A substance with a higher standard reduction potentials, or represented by E right there, would undergo reduction. That means it would gain electron, where a substance with a lower standard reduction potentials would undergo oxidation and lose electron. So here I have one standard reduction potential for aluminum and one standard reduction potential for iron. Which of the two will be undergo reduction or oxidation? In this example, we have aluminum 3 plus gain 3 electron to become aluminum solid with the standard reduction potential of negative 1.66 volt. Where in this case, I have iron 2 plus. Notice how I make mistakes right there. I fix it, and iron 2 plus 2 electron to form a solid iron. And it has a standard reduction potential of negative 0.44 volt. Which of the two has a smaller values? And if the one that has a smaller values, it would undergo oxidation. In this case, we have negative 1.66 volt. It's a lot smaller than negative 0.44 volt. So therefore, this has to be undergo oxidation. Because the lower the standard reduction potential, it would undergo oxidation. Now, what does that mean to this sign? Because this is in reduction form. So to make it oxidation, you would do the opposite, because oxidation is the opposite of reduction. So we would have Al solid equal to Al 3 plus 3 electron. And this is in aqueous state. But what happened to the standard reduction potential? Because we are now looking at oxidation, so therefore the standard reduction, we can change that to standard oxidation potential. Since oxidation is the opposite of reduction, you would have the signs be the opposite of the reduction. So instead of negative 1.66, we would have a positive 1.66. That's all we have to do for identifying the reduction and the oxidation between two half cells. Now, how are we going to interpret this into a voltaic diagram? So we know our oxidation right here. In this case, based on the format of the voltaic diagram, we always follow the direction of the electron. That is, we always draw the oxidation first, followed by the reduction. In this case, our oxidation is Al, and we use the vertical line to represent the state, and we have Al 3 plus. And then the oxidation is separated by a salt bridge, which is represented by two vertical lines. So in this case, we have the reduction. We have Fe 2 plus separated by a vertical line to separate the state of matter of Fe solid. And that's all you have to do to draw the voltaic diagram from two half cells based on their reduction potentials values. In this case, I have calcium 2 plus 2 electron equal to calcium solid, and it has a reduction potential of negative 2.87 volt. And then we have another half cells. So again, this is called half cells because it's happened in another container, where this one is happened in another container, and half. And then the other half cells, we have copper 2 plus 2 electron equal to copper solid, and it has a reduction potential of 0.4. Of course, the negative one will be a lot smaller, therefore this one has to be oxidation. So the low one, again, always undergoes oxidation, so this would be oxidation. So what does that mean? When it exists as oxidation, we are going to reverse everything. In this case, we have Ca solid will produce calcium 2 plus aqueous plus 2 electron. And what happened to the values of the reduction potential when it become the potentials of oxidation? Of course, the signs is going to be opposite. It was negative 2.87, now it becomes positive 2.87. And once we have our oxidation and reduction, we can now write the voltaic diagram, which in this case, we follow the direction of electron oxidation first, separated by a cell bridge, followed by reduction. So we have calcium separate from calcium 2 plus. Then we have the cell bridge that separate the oxidation from the reduction, which is Cu 2 plus and Cu solid. And that would be our answer. This would be our voltaic cells diagram based on the two half cells with their reduction potentials.